Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Today, we're going to be talking about scalability in the internet model, as well as an introduction to some of the ways that we can talk about what it means to be scalable, what it means to be efficient on the internet. And just as a upfront answer to how does the internet scale so much better than the telephone network, it's basically the end-to-end argument in system design. This is a fantastic paper from the 80s that really goes into the set of design ideas and approaches that the engineers used to decide how the internet should be built. And it ends up being a fantastic way to make a network super scalable and able to handle all the amazing things that we throw at the internet every single day. So to take a step back before we talk about how we got this scaling, we're going to talk about what does it mean to be scaling? What does it mean to even be a network? What does it mean to be an efficient network? So when we want to create a network, it needs to have a set of messages that form a protocol. Then it has to have a way to actually send those messages. So we have to have the nodes on different sides of some channel agree beforehand on how they're going to send messages back and forth. And then they need to actually send those messages back and forth. Kind of makes sense, right? So beyond how we make a network work, here we can talk about how we make a network work well. And there's three measures of success. One of them is bandwidth. You can think of bandwidth as the diameter of a pipe, the amount of water that can flow through it, or in this case, bits per second. This is going to be orthogonal to these other things. You can imagine that there's a pipe that has a little bit of water going through it. You can imagine there's a pipe that has a huge amount of water flowing through it. That has to do with the bandwidth, the amount of stuff that goes through per unit time. The next thing we can think about is the delay or the latency. So this is how long it takes something to get from point A to point B. And you could imagine that regardless of the diameter of the pipe, the length of the pipe is a completely different thing. I can have long pipes that are really skinny. I can have long pipes that are really fat. I can have short pipes that are really fat, short pipes that are really skinny, whatever have you. But latency is analogous to the length of the pipe and the speed of the messages flowing through it. So in a water pipe, that's pretty variable, but in computer networks, the speed of something flowing is usually going to be some factor of C, whether it's almost C for optical networks, or I think it's something like 0.3 C for electromagnetic radiation through copper or through air. So in computer networks, the delay is going to have to do with a lot of different things, but primarily it's going to have to do with how long it takes to process a packet at every hop, as well as how much time it takes, the propagation delay of sending that message from point A to point B, which is proportional to the distance. And finally, networks have an error rate, which has to do with how often messages get garbled, how often messages get dropped, how often messages can't be delivered successfully. And this is typically measured simply as a percent. So for every 100 bits that flow through, what percentage of them don't flow through successfully, or you could talk about messages or megabits or megabytes or frames or whatever have you. Some percentage of those things do not get sent through successfully. That's the error rate of the network. And in general, you want your error rate to be low, you want your latency to be low, and you want your bandwidth to be high. But we're engineers, right? We aren't always going to be saying, oh, we just want the best of everything. Who cares, right? Well, maybe in class we think of that, but in the real world, if you're just saying, oh yeah, give me the best of this and the best of this and the best of this, you're going to run headlong into everybody's favorite problem, cost, right? It costs a lot more to make things have lower error rate, or a lot more to get more bandwidth. And in terms of delay and latency, sometimes you just can't even improve it. If you're coming up against that speed of light and how long it takes you to get a message from point A to point B, you can't violate causality and get those bits to their destination faster than the speed of light in a vacuum. And another important part here for our engineering purposes is that more bandwidth is generally better, but it's not always going to be better. If you're using your internet to watch 1080p Netflix, it does not matter if you paid for 25 megabits a second or 2 gigabits per second. You're only using a certain amount. And that's another thing that engineers will usually have to deal with there, where you say, I want to right size my solution to something based on the actual needs. So sometimes your delay and latency aren't really important. Sometimes you only need a certain amount of bandwidth, and more would be good, but certainly not worth the investment. And your error rate should be low, but sometimes it's going to be expensive to keep it really, really low. And you'll say, okay, well, I'm a computer scientist. I can use things like error correcting codes to add a little bit of extra data that allows me to recover messages that got garbled or lost along the way. So now I'm going to introduce the end-to-end argument, but we need to do a little bit of a refresher on what it means to design a network and use a network. At the application layer, we just think we're sending a one message from one process to another process, whether it's like, for instance, an HTTP request. That's not actually what's happening. We're actually sending a message to our router, and then our router sends that message to the internet. It ends up at a router on the other end, which sends it to the ultimate destination. And all of those internet clouds are themselves their own individual networks, and there's different paths between them, and all sorts of things are happening there. So we need to have protocols that standardize these things. We need to have naming so that we know where to get these messages to. We need to have our switching and our routing to figure out how to get to the destination, as well as how to make the next hop to the next router. And we need to share these resources, right? From the previous lecture, we're talking about best effort service and congestion control and voluntarily slowing down so that everybody can keep using the same network. These are resources that are finite that everybody using the network has to coordinate in some way to share and not overwhelm the system. So not only do we have these things that we need, the system is really, really complicated. We've got lots of different places where we could potentially provide naming, or we could provide switching or routing, or even the resource allocation could be decided by different layers of this entire system. And fundamentally, what the end-to-end argument tells us is that in general, it's better to provide as many of these features as you possibly can at higher layers rather than at lower layers. And the basic insight here is that if we're sending messages from one machine to another machine to another machine, and what we care about is the connection between end host A and end host B, if we provide one of these services on a hop-by-hop basis, then unless they're absolutely perfect every single time, the end hosts are probably going to need to re-verify those things at the end. And then you start saying, well, if they're going to verify the accuracy of a message at the end of the process, why do I verify it here and here and here? The end-to-end argument says, hey, listen, push as much of this to the higher layers of your network abstraction because you don't want to have to do the same thing twice. So you only want to provide those services at the lower level if there's a really good reason to do so. So not only is this good at a technical level for just creating a scalable network in terms of how many different users can use it at any one given point in time, we also get the ability to iterate on ideas much, much faster. So remember this diagram from a previous video. When we're thinking at the application layer, we are only talking about those end hosts. Same thing goes for the transport layer. The network layer binds everything together. And then individual link layer networks are on their own and can be completely swapped out on a hop-by-hop basis. If we want to provide a new feature to an end user application, we probably would really want to do that either at the transport layer or the application layer, because doing something at the network layer is going to be super, super expensive. One thing that we've done recently is switch from using IPv4 only to kind of using a combination of IPv4 and IPv6. And that has been decades in the process, and it still isn't anywhere near complete. We're not going to turn IPv4 off anytime soon, possibly never. But the basic idea here is that changing the entire network infrastructure is very, very expensive. That has to do with all the routers everywhere. But changing things in the application layer only really needs to be done at the hosts that want to use that new service. So remember our hourglass diagram where we have that kind of linchpin holding everything together, that IP network layer that gives us specific things. It gives us addressing and routing and best effort service. That's all we get out of the network layer. This allows us to try to get messages from point A to point B. So this is the only design we've been talking about this entire time. And I wouldn't blame you if you thought, well, yeah, duh, that's totally the right way to do it. Why would you do it anyway else? That sounds great. Sounds awesome. Internet, awesome. Let's do it. Ship it. But the cool part here that I I want to focus on is that this is totally not the way that humans have done telecommunications since all time. If we take a look at the telephone network, it was designed in a fundamentally wildly different way that led to some positives, but also led to some kind of negatives, especially when it came to trying to connect computers rather than just humans that wanted to talk to each other. So in the telephone network, there's two very, very fundamental differences that I want to focus on. One is that in the telephone network, all of the decision making about what applications are provided and how to get from point A to point B and how to say when a message starts and stops is all handled by the infrastructure of the network itself rather than the end hosts. The telephone network was not designed with the end-to-end argument in mind. The other really important part of the telephone network is that it's a circuit switch network where you start from one machine, say a telephone, trying to connect to another telephone, and you're going to go through these switchboards, which were either operated by humans or electromechanical switches or effectively computers as we have nowadays, and it would create an electrical circuit between your telephone and the other telephone and just allow you to send those audio messages encoded in electrical signals back and forth. And none of these machines, after that connection was formed, need to do anything besides pass those messages back and forth. And this is good because every single message can go through really, really quickly. The end hosts don't have to really worry about congestion control or connection setup or anything like that. They basically send audio of a special kind to the network. The network does everything for it, and then it just continues sending and receiving audio. That's the way that the telephone network works. But the bad thing here is if one of these hosts goes down, if something bad happens, then that entire connection gets severed. And that is one of those motivating examples of why the internet was designed in the first place. The United States military industrial complex was like, hey, somebody nukes Chicago. We still want to have LA be able to talk to DC and all of our connections go through there. We don't want everybody to have to scramble and figure out how to solve this problem. We'd like to solve this problem immediately and automatically. And that's what packet switching gives us. Packet switching is where we make a decision at every single hop along the way to figure out how to send a message. So as soon as you realize that a certain path doesn't work, you can say, oh, well, here's the next best path that I'm aware of. And nothing has to happen at the end hosts for this change to happen. Just the affected, impacted routers need to make that decision. So another downside of the way that the telephone network was designed with all the smarts in the middle is that if you wanted to do new things with your cool network that you've got, it's going to be pretty hard to do because all of the smarts are in the network, in the infrastructure. So if we look at the evolution of the telephone, right, 1876, Mr. Watson come in here, that was the telephone, and it allowed you to send and receive audio signals. So one of the biggest changes between then and say 1964 was the invention of the touch tone telephone, which made creating those circuits easier. But going up through the 2000s, there wasn't really much advance in what features were provided by the telephone network. You still had these dumb terminals that sent and received audio, and a telephone just like this one in this picture was something that would be on a lot of people's desks up through the mid-2000s. We've now effectively pushed all telephony into a digital world where telephones are just computers that know how to connect to a packet switch data network and do the thing that telephones are used to doing. So if you have something like Vonage, you get that basic idea. You're using the telephone device, but in actuality, you're just using the internet to send your messages back and forth. So this evolution is kind of not an evolution because it was so hard to increase things. Like we had some advancements like the idea of a fax machine, which I think was created before the voice telephone. Fun little trivia fact there. And voicemail, call waiting, things like that. But we didn't really have much advancement in the cool things that your telephone network could do for you, because anything that you wanted to build that would fundamentally change the way that it worked would have to be built into the infrastructure of the entire thing. rather than putting them at the end hosts. So this is the other really awesome part of the end-to-end argument. By pushing as much of that functionality out to the end hosts as possible, this allows you to experiment, this allows you to do something that's relevant here but not relevant everywhere else. Maybe we create an application that's really useful in Chicago or really useful in China. You don't have to wait for the entire network to change its infrastructure to allow your cool new application to run. This both allows you to do lots of different things, and the raw scaling and the ability to do lots of different cool things is part of what made the meteoric rise of the internet possible. So just to reiterate that really quickly, the end-to-end argument and the thin waist hourglass approach to protocol design that the internet uses puts different concerns at different layers. That layering allows us to manage the complexity of these services. That core network layer, the IP layer in the middle, only provides best effort service, but all of the hosts that are using the network voluntarily cooperate in order to make sure that everybody gets good enough service. And putting all of these ideas together gave us the awesome thing that we have called the internet today, that has grown beyond anybody's wildest dreams, is absolutely central to all of our daily lives, and may be killing democracy right now, but we get to look at a lot of cool cat GIFs while it's happening. Thanks so much for watching, and I'll see you next time.